Hello, this is the second part of the Zoom meeting for Monday, January 1st, Math 1401. I want to continue on with finish up section 3.2. So if you want to run right to the end of the first video, end of part one, you can last 2-3 minutes. You can see what we were doing to get down through here. This is the sample standard deviation. It's a little higher than the population standard deviation because you're dividing by one less than the sample size on it. We had created this statistical number line in part one. We had got the population standard deviation to be 75.87, and I was using that. Mean was 148.5, so that goes in the center. So then you're adding the mean plus your standard deviation, one standard deviation to get to 224. So at 224 pounds, you're at one standard deviation above your mean. And then if you go 148, I should put a 0.4. Hope I punched it. Plus twice it, you get to 300.14. And then if you go 148, add 3 times 75.87, you wind up with 376.01 and 3 standard deviations above the mean. All right, well, then all you got to do is change the plus signs here to minuses. You call it back, change the plus to minus, and you wind up with these numbers. 48.4 subtract 3 times 75.87. You can always work your way down just subtracting the standard deviation once here, subtract it twice to get this, subtract it 3 times and you get this. That works too. 148.4 subtract 2 times 75.87 and 148.4, that would be this one. Subtract 75.87 and that gives you here. And the reason that we do it this way is because it really makes explicit this coefficient. Number of standard deviations you're away from your mean. 2 standard deviations here, didn't show a 1 on this one, but 3 standard deviations here. This is called a K value. This coefficient, usually we only use the positive, it's called your K value. Now what this does, this gives 3 distinct intervals. They are named by the positive side. All right. The K equal 1 interval goes from minus 1 standard deviation to 1 standard deviation. And for these numbers, that's from 72.53 to 224.27. I probably should rewrite it on the next page so I got all 3 together, because we're going to do something with this. So the K1 interval, minus 1 standard deviation to 1 standard deviation, 72.53, 24.27. Anybody with a weight in that interval is within 1 standard deviation of the mean. I need to keep that sheet up because I need the K equal 2 interval. Minus 2 standard deviations to 2 standard deviations. That runs from negative 3.34 to 300.14. And for the K equal 3 interval, minus 3 standard deviations to 3 standard deviations, negative 79 to 376.01. Here's the data again, just to remind you. 105, 112, 115, and 300. Okay, to understand the last 2 sections of 3.2, They are all designed to answer this question. Here is the key question. What percent of these data lie each interval? So what we've got to do is count how many of the data lie in each interval. I don't know if you can see the one, I'll look at the k equal 1, and we've got 72.53 to 224.27. We've got the 110 does, 105 does, the 112 does, the 115 does, but the 300 clearly does not. Each of these numbers lies inside, between these numbers, inside this interval, inside the k equal 1 interval. Each of these numbers is within 1 standard deviation of the mean. So answer for k equal 1, 4 out of 5, which is equal to 0.8, which is 80% of the data lie the k equal 1 interval, or lie, within 1 standard deviation of the mean. In the, or within 1 standard deviation of the mean. All right. If you get that idea, maybe we can do k equal 2 without writing so much down. For k equal 2, 3.34 to 300.14, you can see if these 4 numbers are within this, when you widen it out, they're clearly within this. And now look at my 300, and yeah, I'm barely in. So answer 300 is now in. Is 5 out of 5, which is 1, which is 100% of the data is in. Of the data lie the k equal 2 interval. All right. Can you tell the k equal 3, if they all lie within this, and then you extend this out to 376, and they all lie within these numbers, when you go to k equal 3, and this is out 76, this is down to negative 79, can you tell they're all going to lie in this? So same answer for k equal 3, which went from negative 79.21 to 376.01. Same answer. K equal 2. It's 5 out of 5, which is 1, which is 100% of the data, all of them. In other words, all the data lie the k equal 3 interval. Okay, we have these answers written down. We're going to refer back to them. In history, statisticians developed 2 schemes to answer this question. What question? What percent of the data lie the Equal 1, 2, or 3 intervals. Scheme 1. Chebyshev's inequality. It was a Russian guy named Chebyshev in the 1800s. It's written this way, but it probably won't make a lot of sense. At least. And he gave a formula for it. The percent 1 minus 1 over k squared of the data lie the kth interval. Okay, it probably makes no sense at all. So you need Chebyshev table. They put the k number here, put the percent here, and the formula here. Now, you can tell k equals 1, 1 minus 1 over 1 squared is 1 minus 1, which is 0. Does not work. He either never figured it out or there's no answer. It's k greater than 1. So in other words, we can use 2 or 3. You can do 2 in your head. Is 1 minus 1, 1 minus 1/4. That's 3/4, which is 75%. You can do k equal 3 with a calculator. 1 minus 1 over 3 squared. We use 88.9. 0.889, 88.9%. I went that too fast. Let me redraw the table and we'll explain what this means in plain English. Chebyshev's table. Use 2 and 3, the percent, k squared, 75%, that worked out, and 88.9%. What this means in plain English, it is universal truth. For any random set of data the keywords at least, I'll point those out, underline them. At least. At least. This makes these minimum percentages. %75 of the data, minimum, will lie within 2 standard deviations of the mean. He figured this out. It is universal truth, just like pi, just like E. It's mathematical universal truth of the mean. I'll write out the third row. At least 88.9% minimum of the data And I've lost my reason. Let's see if I can get it back.